Hello everyone, my name is Keuntaek and today I'm going to present our paper, Risk-Sensitive MPCs with Deep Distributional Inverse RL for Autonomous Driving. The objective of this study is to learn how to drive, especially how to change lanes in a challenging scenario from recorded human driving behaviors. But instead of directly imitating human behavior, we aim to develop inverse RL algorithms to learn the underlying cost function of the demonstrations. The learned cost function should be directly usable by controllers without any further tuning required. The main challenge of the study is to capture all the cost function in one model. Our motivations come from our experience in MPC and optimal control. In optimal control, designing and tuning a cost function requires a lot of engineering, techniques, experience, and time. For example, in autonomous driving, there's a long list of optimal behaviors we want to consider, and they need to be weighted properly. Through inverse RL, we can automate this process by learning from demonstrations. We solve a trajectory point problem of autonomous driving in a dense traffic highway scenario, and the main problem includes an inverse problem of the cost function of the vehicle and a trajectory optimization problem. There are a lot of inverse RL algorithms introduced in the literature, and the maximum entropy deep IRL is the first work that used the convolutional neural networks to learn the cost map represented as an image. However, MPC fails our task of autonomous driving in a dense traffic if it only has a position cost map like these, because they don't have any velocity information. We introduce goal condition, zeroing, and spatial temporal IRL algorithm to learn a cost function from the human driving demonstration. Given the observation and the goal information, our unit-like cost map model takes their image representation as input and predicts T concatenated position cost maps at once. With the predicted cost map, we find the optimal control and the corresponding optimal trajectory. This slide shows comparison results between cost maps learned by the original MEDIRL in the middle, and our zeroing approach at the bottom, and our spatial temporal approach on the right. As you see, our zeroing method removes a lot of false positives compared to the original work, and our spatial temporal method provides both position and velocity costs for MPC. Our previous work, IRL MPC, was able to finish its task of lane changing in the color simulator. However, it could not repeat 100% of success rate. One of the limitations of our previous IRL MPC work is that the predicted cost maps are deterministic. As the uncertainty assessment is crucial for a safe autonomous driving, without knowing how trustworthy the predicted cost map is, it is difficult to deploy such methods in a safety-critical applications. In this work, we propose 3 ways to improve our previous work in a more risk-sensitive formulation for safe autonomous driving: probabilistic cost map learning, risk-sensitive MPCs, and collision-aware cost map learning. To solve the limitations of our previous work, we first incorporate the notion of the probabilistic learning. Inspired by the concept of the distributional reinforcement learning, where they formulate the Bellman equation in a distributional way, so the value function is a distribution coming from uncertainties in the environment, instead of just a point mass in the traditional reinforcement learning settings. In our work, we aim to learn the distribution of the cost map instead of a point mass determining this cost map. Through this cost distribution, we can handle the edge cases with risk-sensitive controllers. We use the same neural network architectures as our previous work, but now with the Bayesian neural network through Monte Carlo dropout technique. The predicted temporal cost map has a distribution at each pixel. The risk measure we use in our work is the conditional value at risk, CVAR, and we numerically approximate the underlying cost distribution with a histogram with a number of samples in our distributional cost map. And our cost map is composed of pixels with distributions like this. Now with the distribution cost map we learn, in our risk-sensitive MPC problem, we optimize the distribution with respect to the lower tails by computing the conditional value at risk. This slide shows an example of our temporal cost map, our previous work at the top, and the mean and the variance of the distributional cost map at the bottom. The variance cost map shows that the uncertainty lies at the edge of the low-cost region and more on the longitudinal direction. In our collision-aware cosmet learning, we use the other vehicle's future state trajectory to penalize our spatial-temporal cost map when it predicts a low cost, but it actually collides with other vehicles. This additional loss function of false positive costs is added and used to train our spatial-temporal cost map model. We tested with 25 lane-changing scenarios from the NGSIM dataset and saw almost half decrease in the average number of false positives when we use our proposed methods. The color experiments with a lane-changing scenario, our proposed methods at the bottom were able to finish 50 Monte Carlo experiments with only one collision case and reported 16% decrease in the collision compared to our previous work. We also studied the effect of the risk parameter alpha and report the success rates of the autonomous driving task with risk-sensitive MPCs. With a lower risk parameter alpha in our CVAR cost maps, the number of collisions decreased, resulting in higher success rates. Our distributional cost map and risk-sensitive MPC shows much conservative behaviors compared to our previous work, although that resulted in a slower task completion time. Our contributions can be summarized as follows. We reduced false positives and certain predictions in the IRL trained cost maps through the distributional IRL algorithm and a collision-aware training loss function. Our risk-sensitive MPCs with the distributional cost map outperforms other state-of-the-art learning-based autonomous driving policies tested in their color simulator. Thank you very much for your attention.